Catastrophe strikes a major interstate in Connecticut.
It just collapsed. It fell right into the river.
In Montreal, a showcase Olympic stadium turns into an epic disaster.
We were the center of the world, you know, and it was not finished.
In Liverpool, a busy freeway with hidden floors that could collapse at any moment.
That is not currently fit to function.
And a Dutch disaster as a huge levee fail floods a town.
The water here was up to my knees here.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Engineers are always coming up with original and innovative ways to combat the elements. But sometimes even the best laid plans can go disastrously wrong. Like this catastrophic collapse in Connecticut on one of the state's busiest roads.
It was a very fast and inexpensive way to build a bridge like this.
A crossing calamity that ended in disaster.
Every time I go over it, I'm thinking about the tragedy. It always sticks in my mind.
Just 65 kilometers north of New York City lies the town of Greenwich, Connecticut. About an hour's drive from Midtown Manhattan, it's a popular place to live. As journalist Jim Cameron explains.
Greenwich is a very affluent community just outside of New York City, where people will live and then commute.
Taking commuters into the Big Apple is one of the longest freeways in the US, I-95, running all the way from Florida to the Canadian border. And it crosses through Greenwich via the Mianus Bridge.
It's officially known as the Michael L. Morano Bridge, but like many bridges, it takes the name of the water it crosses, the Mianus.
The current Mianus Bridge has been standing since 1992 and carries more than 90,000 vehicles a day. It's a relatively straightforward girder design, but its predecessor, built in 1956, was an altogether much more innovative construction. The original bridge section crossing the Mianus River was a cantilever design made up of 5 sections spanning a total of 196 meters. Sitting on piers, it had 2 anchor spans at each end, a main span in the middle, and 2 suspended or hanging spans on either side, held in place using a system known as pin and hanger. Structural engineer Stephen Ressler explains.
The pin and hanger assembly, as you might guess, consists of pins and hangers. There are actually 2 hangers. You can see one of them here. It's a vertical piece of steel that's connected to the associated cantilever span on top and connected to the suspended span on the bottom by heavy steel pins that run completely through the girder. The hangers are retained in position by steel retainer washers, which are bolted in place both on the top and on the bottom.
One of the reasons for choosing this bridge design comes down to Connecticut's climate. Warm and humid summers combined with very cold winters meant Mianus needed the capacity to expand or contract, depending on the weather.
We have these wild fluctuations in temperature, as high as 100 degrees in the summer, as low as below 0 Fahrenheit in the winter.
The cold will cause contraction and the heat will cause expansion. And engineers know this, so they include clever design solutions to counteract this phenomenon.
The pin and hanger assembly actually has an important practical function as well, in that it allows for longitudinal movement of the bridge in response to changes in temperature. As a consequence of those changes in temperature, The steel members that constitute this structure would have expanded and contracted, and as you can see, the pin and hanger assembly does a nice job of accommodating that longitudinal movement.
But bridges in temperate climates aren't required to use the pin and hanger design. For the Mianus crossing, it may have come down to the bottom line.
They chose hangers because it was a very fast and inexpensive way to build a bridge like this.
For decades, the Mianus Bridge was just part of the daily trek for millions of commuters a year.
If you're driving in a truck between New York and Boston, you're probably going on this highway, over that bridge, over the Mianus River.
On June the 28th, 1983, at 1:30 in the morning, 2 tractor trailers and an automobile were on the eastbound section of the Mianus Bridge when the impossible happened. The entire 30-meter span of the suspended section collapsed dramatically and without warning, falling more than 20 meters into the river below, taking all 3 vehicles with it.
It just collapsed. It fell right into the river.
This failure was so sudden. There was no warning. The section of the bridge deck just dropped.
Another car was unable to stop in time. 3 people were seriously injured, but even more tragically, another 3 lost their lives. Attorney Richard Silver witnessed firsthand the devastating scene.
When I went to the scene to view the tragedy, which it was, there was masses of steel. The section of the bridge collapse was in the water. The trucks were visible. You could see the awful impact of these vehicles going over the bridge.
The disaster shook the town. Some had escaped tragedy by just a few feet.
The drama was horrendous. After the bridge collapsed, I interviewed a number of people who drive over that bridge every day, who luckily had been able to stop before the disaster. And of course, what went through their mind, it could have happened to me.
In the wake of the disaster, an investigation looked into what had gone wrong. An inspection of the wreckage revealed that the pin and hanger connections were heavily corroded. But what had caused them to rust so badly?
Like anywhere that has regular cold winters, road surfaces are regularly salted during the winter to keep them safe for motorists. When it rains, the salt washes from the road surface and onto the bridge's structure. Salty water and steel can be a recipe for disaster.
To reduce the risks of corrosion, a drainage system was built into the bridge to carry not just salty water, but debris away from the pin and hanger system into a gutter to minimize the danger. But the investigation revealed that this crucial design feature had been compromised.
So about 20 years after this bridge was originally built and constructed, it came time to resurface the roadway. And that meant laying new asphalt. But in the process of doing that, they plugged up some of the drainage holes that were crucial to water in the winter from salt water being able to drain off of that bridge. By plugging up those holes, water found its own level and it drained down past the supports, the pivot and the hinge that were holding the bridge in place. And it caused the pins that were literally hanging that bridge in place to start to rust.
Corrosion accumulating behind the upper retainer on the pin and hanger assembly right here started to pry the retainer off of its pin and ultimately did in fact remove the retainer. It forced it off of the pin. At this point then, continued corrosion resulted in the hanger itself being forced off of the pin. And when that process was complete, this hanger became physically disengaged from the structural system and was no longer participating in holding up the suspended span.
Investigators believe that this displacement could have occurred weeks or even years before the collapse. Now engineers had to figure out how to fix the problem. After the tragic collapse of the Mianus Bridge, investigators found that a potential problem may have been hidden for some time. A fatal flaw that went undetected until it was too late, and was possibly triggered by just one very ordinary event. Structural engineer Stephen Ressler explains.
The critical moment, 2 heavy trucks happened to have driven onto the center span at the same moment, and that particular extreme loading was enough to cause the remaining pin and hanger assembly to fail. Once that second pin and hanger assembly also failed, the center span could no longer carry load, and the entire suspended span collapsed down into the Mianus River.
The investigation found accelerated corrosion caused by a lack of drainage and excess salt was the most probable cause of the disaster. Many also believe that if the corrosion had been spotted earlier, this tragedy could have been avoided. The collapse cut off the main artery between Boston and New York, rerouting 90,000 vehicles a day and causing month-long traffic jams. So when it came to the new bridge, engineers weren't taking any chances.
The bridge had to be rebuilt, this time without a pin and hanger system, but with a continuous girder and floor beam design.
They replaced it with a girder structure that sits on pylons in the river. So rust is not going to cause that bridge to collapse.
Not only is the Mianus Bridge more solid than ever, its failure alerted engineers to a problem that could be pervasive across the country.
It reawakened concern about the safety of bridges, and that there was now a requirement that they be inspected more often.
Some estimates suggested that at the time there were about 60 pin and hanger bridges in Connecticut alone, and around 2,000 across the US.
Throughout the entire country, there was an examination of these pin and hanger assemblies. It's to my knowledge that this design was not utilized again.
When it comes to big engineering, sometimes innovation can really pay off. But other times it can turn to catastrophe. Like this cutting-edge construction that put Canada on the map for all the wrong reasons.
We were the center of the world, and it was not finished.
A space-age design that suffered from a failure to launch.
This was a construction that went way off track and more than $1 billion over budget.
And a revolutionary roof that 4 decades later still can't cope with Canadian winters.
This is one engineering catastrophe that doesn't look like it's ever going to get fixed.
Located on the St. Lawrence River, Montreal in Quebec is one of North America's most diverse and European-inspired cities.
Montreal is Canada's second largest city and widely considered the country's cultural capital. It's a real melting pot, with more than 60% of the population speaking French.
In 1967, Montreal hosted the International Expo, or World's Fair. With over 50 million visitors, it was widely considered to be the most successful World Fair of the 20th century and really put the city on the map.
So when it came to hosting the world's most diverse event, Montreal had that certain je ne sais quoi. And on May the 12th, 1970, it was awarded the 1976 Summer Olympics. The city had bold plans for a show-stopping stadium, as urban planner Sylvain Lefebvre explains.
This is the Olympic Stadium. It was very audacious from an engineering point of view.
The groundbreaking stadium would hold up to 76,000 people in stands supported by 34 self-stabilizing cantilever arms. Looming large over the structure at a 45-degree angle and 175 meters tall would be a modernist tower, 3 times the height of the Leaning Tower of Pisa.
we had this magnificent stadium and very ambitious from an engineering point of view, with the biggest and tallest inclined tower in the world.
And their ambitious plans didn't end there.
The centerpiece of any Olympic Games is the stadium. Montreal wanted a landmark statement, especially when it came to the roof.
Like a lot of Canadian cities, Montreal can experience very harsh and snowy winters, typically lasting around 5 months. So to make use of the stadium all year round, a roof was essential. But Summer Olympic mandates require the athletic events to take place in the open air. So designers came up with a bold and revolutionary idea: a retractable roof.
Retractable roofs on stadiums are commonplace now, but back then, this technology was very much in its infancy.
The retractable roof would consist of an orange and silver membrane larger than a football field, weighing around 70 tons, and supported by 26 steel cables. The plan was for the enormous fabric roof to fold away like a giant umbrella inside the huge tower. Because of this cutting-edge design, the material had to be both flexible and strong enough to stand up to Montreal's snowstorms, yet light enough to be suspended across a huge area. The material they chose was Kevlar. At the time, Kevlar was a relatively new, super strong and very light synthetic fiber. But it had never been tested on this scale before.
Kevlar is great if you want to stop a bullet, but maybe in hindsight, not so brilliant if you want to build a retractable roof.
Even before construction had started, things began to go wrong.
The stadium was meant to be a real showstopper, but it was plagued with problems right from the start.
Despite Montreal being awarded the 1976 Summer Olympics in May of 1970, the final designs for the ambitious stadium weren't submitted until more than 2 years later, meaning work on the site didn't begin until late April 1973.
The delays meant they now had less than 3 years to pull off one of the most ambitious projects of its kind.
By July 1976, the landmark tower was only 72 meters high, less than half its intended height, and the revolutionary roof was nowhere in sight. But the Olympic Games wouldn't wait.
The eyes of the entire world were on Montreal and its show-stopping stadium. There were 73,000 people in the stadium, including the Canadian Prime Minister and even the Queen of England. The only thing missing was the roof.
This was the first time in Olympic history that the stadium wasn't ready on time.
When we had this overture open ceremony for the stadium, we were the center of the world, all on TVs and everything, and it was not finished.
After the Olympics, the stadium was used for a variety of events and sports and became home to baseball's Montreal Expos. But incredibly, it wasn't until more than a decade after the Olympic athletes had all packed up and gone home that the tower was finished and the retractable roof hoisted into place. Although it looked impressive, it was far from perfect. Architect Pierre Utras explains.
It was made of Kevlar, coated with vinyl. But this roof had some, would say, design flaws. The roof as a whole would tend to lift up under wind load and sink down under dead weight load like snow. There was what was called trampoline effect under the wind.
This trampolining effect meant that in order to remain stable, the roof had to be pulled very taut. But this was creating issues of its own. The roof didn't just have major wind problems, it was ripping too.
There were certain circumstances where the roof would lift up and then come down suddenly and break at the stress point, and once a rip starts, there's no way to stop it.
Despite all its problems, authorities persevered with a clearly failing retractable roof for more than 20 years, before repeated tears finally kept it closed for good. But the city wasn't giving up on its stadium, and they were determined to try again. In 1998, the retractable roof was finally replaced with a new fixed one at a cost of $26 million. This time, instead of Kevlar, they used Teflon. But designers failed in this material choice as well.
The new roof was meant to fix the problems of the past, but it still proved a massive headache.
The problem was that the new fixed Teflon roof still had to connect with the original roof's framework.
This actual roof is made with fiberglass reinforced Teflon. On the stadium, the structure itself is made of cable. And since of its very large area, it is subjected to movement. And unfortunately, fiberglass reinforced Teflon cannot stretch.
This time, although it looked like they got the right material for the job, it was still being held up by the original structure that was designed to support the more flexible Kevlar.
In 1999, just a few months after installation, one of the Teflon panels collapsed under the weight of snow, while 200 people were preparing for a car show on the stadium floor below. Luckily, no one was seriously hurt, but this wake-up call meant that authorities decided the stadium would be closed down when only 3 centimeters of snow was forecast. Not ideal in a city that can get 5 months of snow a year.
In the winter months, Montreal averages around 15 inches or 40 centimetres of snow. So to build a stadium roof with a snow load of just over an inch or 3 centimetres seems crazy.
The roof has been holding for 20 years, but the stadium is closed down in the winter. Stresses sometimes can make micro openings of the mesh of the canvas itself.
And hundreds of holes were opening up in the roof every year.
Once the rip count got close to 8,000, they knew it was time to go for another roof.
Yet again, millions had been spent on a roof that simply couldn't stand up to Montreal's harsh winters. Despite its troubled past, and while sadly no longer home to the Expos, the Montreal Olympic Stadium still hosts a wide range of events from all over the world. So, in 2017, the Quebec government decided that the stadium should get its 3rd new roof, this time at a cost of $250 million, the original budget of the entire 1976 Olympic Games. With all the repairs, alterations and delays, costs have literally gone through the roof, rising to well over $1 billion.
Despite all the problems, overruns, and disasters, the city still deserves a stadium and a roof they can be proud of.
The stadium may have been one of Canada's most expensive and biggest engineering catastrophes, but the bold architectural design of the Montreal Olympic Stadium still stands out on the nation's skyline. Although the roof remains a work in progress, hopefully this time it will at least keep the snow at bay.
Even now, the new roof has been delayed and isn't due to be completed until 2024, almost 60 years after the city hosted the Olympics. For this particular construction, it has definitely been more of a marathon than a sprint.
When it comes to big engineering, sometimes problems can lay hidden for years. It's only once the flaw is discovered that we realize we were in danger all along. Like this elevated roadway in the UK, threatening to collapse into a historic downtown.
It might look solid, but it's a disaster waiting to happen.
A freeway with fatal flaws that remained hidden in plain sight for decades.
Engineers had suspected the problem for years, but no one saw this catastrophe coming.
And a city's bold decision to protect its residents. Liverpool in northwest England is one of the UK's most historic and celebrated cities.
Liverpool is famous for being the home of the Beatles, but there's much more to this city. It's long been a key trading port with its heart down by the docks.
In the 1960s, as the Beatles were taking the world by storm, the city was also on the rise, and it needed an infrastructure allowing it to grow into the future, as local government official James Noakes explains.
Liverpool in the 1960s was a real hip and happening place. It really was a place to be. And so as part of that, people had this vision of an almost sci-fi approach to how we dealt with transport. And that was large motorway infrastructure right in the heart of the city.
To get with the times and ease congestion, authorities came up with a radical idea. Instead of going around the city, they would go directly over it, with not one, but two elevated freeways, known as the Churchill Way flyovers.
In order to take cars away from the mouths of the tunnels underneath the river, a plan was devised at the beginning of the 60s to build two huge concrete structures.
Each of the two 240-metre-long elevated freeways were made up of 10 concrete spans, creating a continuous 7-metre wide deck, held up by a series of single concrete columns, 1.5 metres in diameter, supporting nearly all of the weight. But the supporting columns simply wouldn't be strong enough to hold deck spans made of solid concrete. So engineers' plan was to make the insides hollow.
Engineers built wooden molds and poured concrete over them, creating hollow decks with the wood left inside.
This wasn't inherently a problematic design, but it did have some risks. Because the bridge design didn't call for manhole covers, which would allow the inside to be monitored during and after construction, if the wooden boxes were compromised while the concrete was being poured, the structure could become too heavy for the supporting columns to hold. Opened in 1970, the elevated freeways quickly became integral to the city's transportation network. Built to have a lifespan of around 70 years, after just 10, there were already signs that both roadways were struggling to cope.
In the 1980s, engineers inspecting the viaducts found crumbling concrete and signs of rust. Worrying with any structure, but particularly with bridges or viaducts carrying heavy traffic over busy roads.
But a much more menacing and potentially fatal problem was lurking within the bridge spans. And without a means for internal inspection, engineers wouldn't realize the danger for decades. Sometimes potential dangers are hidden in plain sight, like here in Liverpool, where for 45 years, an ever-present danger was a part of commuters' and pedestrians' daily lives. Yet, in 2016, new legislation was passed, requiring internal inspection on all major highway structures. It was finally time to go inside the Churchill Way flyovers.
Engineers drilled through the concrete to inspect the insides of the decks, and they got a bit of a surprise.
During the initial construction, as the concrete was poured, some of the wooden boxes creating the hollow decks had burst, allowing more concrete to pour in than engineers had ever calculated for.
No one knew it had happened, but the extra weight was putting huge, unexpected strain on the structure.
The decks that had been carrying traffic over the city for decades were much heavier than the concrete piers were ever designed to cope with. These elevated freeways were ticking time bombs. On September the 28th, 2018, the roadways were closed while over 140 detailed safety checks were carried out. The conclusion was damning, as engineer David Slevin explains.
The assessment of the structures has concluded, based on the condition of the inner webs of the unseen parts of the structure, that it's not currently fit to carry the actual highways loading that it would need to carry to function as the highway that it needs to be.
What they found was truly shocking. Corrosion, poor quality concrete throughout, and worst of all, serious cracking. The structure was so damaged that it couldn't be strengthened and was beyond repair. Churchill Way was closed for good.
They calculated that the structures could safely support their own weight, but not the traffic that had been thundering over them for decades. It's a miracle that they're still standing.
The city had avoided a major catastrophe. But with two fatally flawed and potentially dangerous freeways running directly over the city, the next problem was how to get rid of them.
Traditional demolition on a structure like this would look like large excavators with large breakers, lots of noise, lots of dust, lots of vibration. It's not a practical option to do traditional demolition on this structure because we're in a city centre environment.
Putting some of Liverpool's most historic buildings at risk wasn't an option, so alternative methods had to be explored.
The vibration risk is something that's been considered from the outset of this project. The selection, we have multiple controls with numerous noise, dust and vibration monitors throughout the surrounding buildings.
The solution experts came up with was as surprising as the original construction itself. Rather than demolition, they opted for deconstruction.
What we've devised as engineers is a series of cuts and removals of individual sections. They're cut in situ as they sit on the current structure. They're lowered to the ground, cut to smaller sections and taken away.
To minimize disruption, the 50-year-old spans would be slowly taken down in 24-meter sections. Each span weighing hundreds of tons would be temporarily supported before being cut free and moved onto a special transporter, where it would be lowered and taken away to be demolished. The goal was for the bridge deconstruction to be completed by the end of 2019.
The viaducts will soon be gone, but hopefully planners will see an opportunity to bring the space to life in a whole new way.
Whatever they come up with, Liverpool's engineers certainly have an interesting road ahead. Engineers need to understand the reliability of their building materials and how they will react under all conditions. If they fail to consider a scenario, no matter how unlikely it may seem, a catastrophe is in the making. Like this engineering disaster in the Netherlands.
For a famously low-lying nation, this was terrifying.
A fail that almost flooded an entire town.
With 600 homes in Wilnis, the thought that this levee could fail was almost inconceivable.
The water here was up to my knees here.
The Netherlands is famously flat, with a large percentage of land actually at or below sea level. It's been carefully engineered to sustain a population of 17 million. They have a saying, God created the world, but the Dutch created Holland. And they did it all with levees or dikes. Engineer André Collewin explains.
The Netherlands are built basically in a marshland. The name says it's Netherlands, it's low country, and without dikes we wouldn't exist.
Dikes are a form of man-made levees that are designed to channel water through canals, protecting the land that surrounds them. Holland's dikes date back to medieval times, but in more recent years they required an overhaul.
This desire to control the flow of water is rooted in an event which traumatized the entire nation.
Following a huge storm in 1953, which killed 2,000 citizens, the Dutch government, vowing to be better prepared next time, began investing billions of dollars in an unparalleled network of dams, levees, canals, pumps, and storm surge barricades.
Control of water is of extreme importance to the Netherlands. 2/3 of the country is protected by dikes.
The updated system keeps the nation safe and dry.
If these defenses fail, there's nothing to protect the people's homes from the water.
Many of the nation's dikes were created as a byproduct of fuel mining. But this isn't your average fuel source.
Peat is often thought of as the forgotten fossil fuel. It's found in wetlands such as bogs, fens, and swamp forests. But when it's dried, it burns long and slow.
Peat is essentially a buildup of decaying vegetation and organic matter. It forms over thousands of years, resulting in a material that can be used for many different purposes.
The Dutch have been digging up peat since the 17th century, firstly as a form of fuel, and then as animal litter, and most recently to help cultivate their gardens. These peat mines were then often converted to dikes or small levees.
Just like the dikes in the sleepy town of Wilnis. Local journalist Peter Bakker is a lifelong resident.
In Wilnis, it's a sleepy city. Nothing happened normally here. A tough area for doing some reporting work.
However, in August 2003, the serenity of sleepy Wilnis was disturbed.
It was 2 a.m. I woke up and there was something happening in Wilnis. I look at my pager, I jumped up my quad and go to Wilnis.
When Peter arrived at the canal, he was shocked at what he saw.
There was a lot of people on the streets. A lot of water was streaming out of the dike, and it was like an ocean. A lot of water, every water was here, was going down to the village. It was very strange.
The sleepy town of Wilnis had been rudely awakened by a raging flood. The entire town was under threat. Although exactly what caused the disaster wasn't clear. In a town only made possible by dikes, controlling water flow was critical. Peter Heidemer is a local who lived through the ordeal.
I lived in that house and I heard voices during the night, a lot of commotion coming from our neighbors who are living there. So I walked upstairs to the highest level. Because of the moonlight, you see shattering of water. And that's actually really strange because there is no water here normally. I walked out of my garden and after a few steps, the water was here, ankle height, something like this. And I walked further. When I was around the corner, the water here was not ankle height, but it was already up to my knees here. It's like a lake, and that's really frightened me.
By now it was realized that a large section of Wilnis's dike had catastrophically collapsed. Local resident Hanny Visser remembers that day.
I was looking out my window and I said, wow, water, what's this, what happened? Certainly the houses here till the end, the big houses, they had the most damage. And the bungalows, of course, because everything was underwater.
Things were going from bad to worse until local contractor Koos van der Vaart spotted the problem.
I came here, there was a lot of water floating into the houses here below. I speak someone from the fire department and I said, no way we can stop that water here because the water was flooding all the time. We have to be quick, but this side was already destroyed. But that side, we have to be quick to avoid more damage.
Koos came up with an ingenious plan to stop the flood by creating a makeshift dam upstream from the collapsed dike.
This was the bridge where we can stop the water. It was strong and narrow, so we have the possibility to stop it. We take iron plates and clay, so we could make a watertight emergency dam.
Koos's makeshift dam worked out, preventing further devastation. Finally, the flood levels began to fall, and the townspeople began to return to their homes and assess the damage.
After those 2 days, we came back and we found out you see dead fishes laying in your garden.
Some residents were more fortunate than others.
We were actually really lucky. We didn't have water inside our houses, only in our garden.
For many, the situation was much worse.
The houses are flooded, also the basement, the first floors, and luckily there's nobody hurt and nobody died.
As the waters began to recede, the people of Wilnis felt very lucky. They were terrifyingly close to losing their town and possibly their lives.
In the wake of the devastation, investigators began to explore what had happened. The answer was far from straightforward. And although some suspected the Wilnis dike had been compromised, it had a reputation of being unbreakable.
What added to the initial confusion was that this dike had recently proved highly effective when handling some of the heaviest sprains Holland had seen in years.
1 year before the disaster happened, the dike was overtopped because of heavy rain, and it did not fail. It was just safe enough. So everybody thought, well, okay, it's water relief, it's safe enough.
So what had caused this veteran levee to crumble? When building the dike, engineers had taken water into consideration, but not the sun. In recent months, Holland had experienced a period of unusually hot and dry weather.
The combination of drought and sun dried out the peat. Cracks then formed within the peat layer, and when the water finally arrived, it traveled through the cracks under the peat.
Not only was the peat no longer watertight, its integrity had also been weakened.
Investigators worked out that the dried peat was about 20% lighter than normal peat, and the pressure of the water underneath it forced the peat to break off and lumps floated to the surface. This weakened the dike enough to make its collapse inevitable.
The water flowing through the cracks in the dried-out levee caused it to erode. With constant pressure, the dike began to crumble, resulting in a total failure.
The failure at Wilnis was a huge surprise to everyone involved in dikes, because normally all causes of failure of dikes were known to be by water, not by drought.
Ironically, it was too little water rather than too much that caused this catastrophic collapse. In the aftermath of the flood, Wilnis's dike needed to be rebuilt. This time, engineers chose not to put all their faith in peat.
The solution to this type of problem is putting a blanket of clay on the peat dikes, preventing the drying process, and also giving some extra weight to the dike.
Clay is less porous than peat and exhibits a higher load-bearing capacity, ensuring stronger foundations for the new levee. Not only that, extra reinforcements were added in the center of town.
Before all the problems, the dike was only of peat. Now we have a beautiful dike with concrete and steel, and I think we have the best and the safest dike in all the Netherlands.
While it took months for the town to recover, there were no fatalities, and that's largely down to Kossel's quick thinking.
We were successful. We stopped the water at this place. Me and a lot of other people who also worked a long night.